So I feel that question specific, problem specific, don't understand the max, but we try our best. Okay, we try our best. So let us just establish everything proper before we begin. So obviously we use a binary search, and the second method can definitely use a brute force. And for conditions, definitely you can use after or before. So when we dive deep question specific, I will say we're not so sure about everything, but okay, we see here. So what they do is basically median of two sorted arrays. So basically you combine A plus B, and then you try to find median. That's the main goal. That's the main goal. So obviously with that said, we definitely want to total up all the elements, which total up to be 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So they actually do remove one element, which I don't know why, but we trust them. So obviously when you halve them, it will become 6 6, right? 6 6. So to that, I think that's why they split into 4 2. Cause obviously here the center is half is 4, here half is 2. So make a lot of sense. So then we proceed, draw it out, right? We draw it out, split them half. Okay, now what they do is they compare is this value less than the opposite array, the number. True, for A is true, but for B, 4 and then the outside of the barrier is not true. So problem, now problem is either we need to adjust the B or we need to adjust the A. Interesting. How do we know which to shift? Cause what I know they do is they actually expand here. But question is, why can't they actually expand here? Is cause here true already? Cause for A is true, therefore I don't need to change B. But for B is not true, therefore I need to change the other piece, which is A. Okay, so A need to change. Alright, cool. Okay, maybe that's the reason why. So A has to change. Okay, A has to make it bigger, because right now the B is saying that, hey, my value less than your right element or not, and not true, that means your R is not meeting the standard lah. Your this one is not meeting the standard. You need to make it more, make it better. So to me, you go here, that means you are making your item to become better. So therefore we need to shift it. So my L, need to shift here. I just don't know how to actually expand. But I know that what they do is they put the L here, but they put the L and the M here, but why ah? I actually don't know, but intuitively speaking, if you were to ask me, like before anything else, before watching them, I would say that I'll put the M here, okay, but my L and R still kind of like sort of exist, but I just kind of say that, hey, can borrow your space or not, Mr. R? Borrow your space, 勉强 a bit. Let you take this small space, then my left graph take this space, okay? Please, borrow a bit. And then now my this question is gonna ask again. Is my B less than or equals to R? Fulfill criteria. 4 compared to 4. Wow, hang I fulfill criteria, right? I fulfill criteria. So with that, so it's 3 now. We need to transform to half 6, right? Interesting. So I expand here 3, I also need to decrease the other side, even though the criteria do meet. So now I ask the question again. My B less than your R or not? Then answer is yes. And then my A less than your R on your opposite side or not? And answer is yes also. So very good. So right now we just need to find the median. That's all we need to do, right? We place the boxes correctly this time around. So basically we for median is basically a center number. So we need traditionally speaking, it's basically a bunch of number. So 1, 2, was 小 hard to write. Oh my god. But okay, 1, 2, 3, 4, 5. 1, 2, 3, 4. So say for example like this, I need to take a 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We need to take these two value and then divide them. So got A and the B, right? A plus B divided by 2. Intuitively speaking, median, that's how you actually calculate. So we bring operation X, and this is operation Y. How can we translate this operation X to operation Y? So we need basically what we're trying to say over here is that if you were to see this one, is basically the maximum of left box. Max of left box. And here is minimum of right box. That's what we are going to do. This one is A, this one is B. So from operation X, let's transfer to operation Y. We need the max of our left box. So basically, the new left box will be 3 plus 3. So 3 plus 3 divided by 2. Then the minimum of the left box will be 4 plus 4 divided by 2. So this one 3, this one 4, then 4 plus 2 divided by 2, 3.5. So this one is our result value, and send back to your system. Here you go. This is your median for your 2 sorted array. So I think that's pretty much it. So I think the complication part is this, that it's actually very tricky, because you need to rearrange. I think when we talk about operation specific, it's you need to understand X, you need to understand Y, you need to know how to actually translate, you need to actually be able to come up with a reference X, operation X, so that you can actually translate to your Y, and then start performing all these different operations, and at the end returning back the result. I will say that the complication part is this is that I think first and foremost, what they did here is very smart. They have like 13 elements, very hard to count, very hard to split half, right? Very hard to split half. That's the first thing. So what they do, they split into half, so that they can get like a nice number, a 6, half 6, right? So that's one, right? It's like manipulate numbers, that's what we call it. That's what they do over here. And then second thing, the complication comes over here, is that how can you question your boxes that they actually share the same rule? So manipulating the boxes, for the 2 arrays. I think that's what is so tricky about manipulating the boxes. Really difficult. In my opinion, I wouldn't even know if they didn't explain to me at all, right? And the third complication, like what we said, the operation Y, drawing the reference for operation X, and then start referencing your operation Y and the X, so that you know how to come up with this, and then reference it to Y per se, and then be able to do this calculation and return this final result over. I think all these things makes this question specific problematic for me and you, or maybe you're smart, I don't know. But when we talk about like the mechanism, the properties, definitely we use binary search, and binary search, obviously we use the LRM method for us to actually do our calculation, whatnot have you. And coming to that, I think we'll talk about spell, is that why not, actually you asked me to do a brute force for this one. How the hell do you actually do it? You count how many number over here? Sure. There's 8 number over here, there's 4 number over here. Sure. I mean, I can plus every single value. I actually don't know how you actually brute force this thing though. Cause the probability of this thing, right, the nice thing about it is it's always like trying to find the center value, and I think brute force, or you can't find the center value at all. Am I right or am I wrong? Like this whole question, right, is just fully leaning towards binary search, right? It keep on wanting to find the center value, right? I mean, okay, I mean, sure. I mean, brute force, I think you can like check. Okay, is one or two, which one smaller? Then you say, okay, maybe this one small, this one big, this one small, this one big, and then you keep comparing one another until you find sort of like the centerpiece. And then once you find the centerpiece, maybe say you find until two centerpiece, you plus them together, then you divide by 2. I mean, sure, you got how many elements? You got 13 elements. Why not have you compare each and one of them? I think, or you keep comparing like that, right? Is it like n power of 7? I think it will become like a n square, big O of n square. That's my guess. That's my guess. It's just hypothetically speaking, I think it will go under n square. And this one, binary search, like the way you keep on doing this operation, why not have you mostly log n operation, but you keep comparing here and there, you do all this complication, maybe it will multiply by maybe say m, where m is the number of times that you need to actually do the comparison. So my theoretical guess is like something like that, m log n, big O of m log n, maybe, where m is the number of like times that you need to tweak things and then do binary search again, and then finally you need to plus this value, returning the final results. That's my argument for this per se. So yep, everything comes to an end.